Today we're going to talk about chemical bonding, and if you are watching this video, that means you were absent, you were either gone for band or maybe you were sick. So if you were gone for band, hopefully you guys did well. If you're sick, hope you're feeling better. And I'm sorry this is not the perfect lesson, but it's better than nothing at all. So what we did, we took notes over chemical bonding today in class, and I have uploaded this PowerPoint so you can print it off and follow along. But we talked about why atoms bond to one another, and the reason atoms are going to bond to one another. You're going to get the shortened version of this lesson. I'll just warn you ahead of time so you can pause and fast forward and stop however you want. But the reason that atoms are going to bond to one another is because they're trying to have what we call a complete octet. They want 2 in their S's and 6 in their P's. And that's going to make them stable. We call this a noble gas configuration because if you think of the noble gases all have 2 in their S's and 6 in their P's. So that's what makes them so perfect, and that's the reason they don't bond with other things. In order to achieve this, atoms will either gain electrons, or they may lose electrons, or they may even share in order to get to this octet. That's why they don't stay in their natural state. That's why we find all these compounds, such as water and sodium chloride, because they have done some things with their electrons. And again, the story is all about the electrons. Protons are not involved in this. And we have 2 main types of bonding. The first type is called ionic, and an ionic bond is actually between a metal and a non-metal. And what happens is the metal actually has extra electrons hanging around in his outer energy level, and the non-metal doesn't have quite enough. And so they'll kind of do an exchange type thing where the metal will give the non-metal its electron. When an atom gives away an electron, it actually becomes positive. When a nonmetal gains the electron, it becomes negative. And opposites attract, and they kind of stick together, kind of like static electricity, where if you've ever had your sweater and you pulled it out of the dryer and it's got your socks all stuck to it, it's kind of got that static charge. They're kind of stuck together. So here's what you would write. It occurs when atoms transfer their electrons, one actually giving the electrons, the other's taking the electrons. One atom becomes positive and one becomes negative, and just like in life, opposites attract, and they're going to stick together and form a compound. And one thing I did with the class is I drew out, and where they could see, if we had, for instance, potassium, which has 1 dot for its dot diagram, if we wrote out its electron configuration for potassium, it would back up to argon, and it would be 4s1. And then I did fluorine with them, and I actually switched colors where they could see. So let me switch colors real quick. We'll make it pink. We had fluorine, and fluorine is, if we backed it up to its nearest noble gas is actually helium. He would be 2s2, 2p5. Now if we look at this, this guy only has 1 electron in his outer energy level. So he could, in order to have 8, because they want that octet, he could either gain 7 or he could lose this 1. If he were to lose this 1 electron, look here, he's going to look like argon. And if he looks like argon, then that's a more stable configuration, looking like a noble gas. So he's actually going to lose this electron. And so I'm going to go over here to this one, and I will show you where the electron's going in a minute. This guy has 7. He wants 8. So he's actually going to gain an electron. If he gains an electron, this is going to change to a 6. Can you see that 2 plus 6 makes 8? It's going to make him have 8 electrons. So if we draw this out, this guy originally had 7, a valence number of 7. 2, 4, 6, 7. What's going to happen is that this electron is going to go right there, and it's going to fill that shell. Well, this guy's no longer going to have it because he's actually going to give it to them. That's going to cause this atom to be charged, a charged particle. It's actually going to cause this particle to be charged as well. It's going to have a negative charge. We say it has a -1 charge because it's gaining 1 electron. This has a +1 because it's lost an electron. And so what happens in an ionic bond, one actually transfers its electrons, and that will cause this positive ion and their energy levels do not overlap, so they're just going to be close together. It causes them to kind of stick together and make a solid crystal, kind of like a salt crystal. Unfortunately, this fluorine doesn't just like that potassium, it also likes this potassium. And that potassium doesn't just like this fluorine, it actually likes this fluorine over here. So what happens is these guys make crystals. And so this is an ionic compound, and ionic compounds tend to make crystals, kind of like salt crystals. And so that's what it looks like there. So our next type of bonding is actually called, well, before we do that, this actually occurs between a metal and a nonmetal, or an element and a polyatomic ion. And you guys have your polyatomic ions coming up very soon. If you're an A-Day student, your polyatomic ion is on Friday. If you're a B-Day student, your polyatomic ion quiz is on Monday. If you're in 7th period, your polyatomic ion quiz is on Friday. Okay? So then we go on to covalent bonds. A covalent bond, on the other hand, is when electrons are actually sharing their electrons. The energy levels are overlapping, and one energy level is going into another. This is going to occur between two or more nonmetals. The example that I gave them in class would be, a good example would be like carbon. Carbon has a valence of 4. He loves to share. Carbon loves to share, and he actually will share with 4 different atoms. But that's not going to show up. Let me grab pink. I need to pull it to the toolbar because it keeps disappearing. So if I put chlorine here, chlorine has 7 valence electrons. I'm making them in pink. So these are chlorine. The pink ones are chlorines, the blue ones are carbon. This carbon's willing to share one of his electrons with this chlorine. Now when they share, it starts to become, it's not mine, it's not yours, it's ours. It's kind of like when you get married, it's not my money or your money, it's our money. This carbon's sharing this one, but now carbon's not quite happy because he doesn't have 8. He's actually going to need a few more little chlorines to share with. So he can share with this chlorine, and up here he can share with this chlorine. Notice I'm always drawing just 7 pink dots, and he can share 7 here. And this is a covalent bond. Different than an ionic. They're not charged particles. They're actually sharing their electrons. This is CCl4. The 4 is for the 4 chlorines going around. This is called carbon tetrachloride. And that's a covalent bond. And it occurs between nonmetals. There's carbon and chlorine, which are 2 nonmetals. What you missed today was me just defining ionic and covalent bonding and just being very general. So on your quiz you need to know the difference between an ionic and a covalent bond. But then we also learn how to name and write formulas. So we spent some time just talking about an ionic compound, and we just went through some definitions that we've talked about before. The definition of an ion, an atom that is either gained or lost an electron, just very general, being a charged particle. And then we had definite types of ions. If it was a positive ion, it is called a cation. And I told them that they could remember cation because it's the one that makes the T, is a cation. And this is when they lose electrons, they actually become positive, because what's happening is you're losing a negative thing, and 2 negatives make a positive. And you need to know that metals are the ones that are going to form the cations. Metals are forming positive. Anion, on the other hand, and it is pronounced anion and not anion, is an atom that has gained electrons and actually has a negative charge. Nonmetals are going to form the negative ion. So we're going to be looking at positive ions and negative ions. And these are only for ionic compounds. They're not for covalent compounds. The other term that we learned was oxidation number. That is the charge that the ion is going to make when it gains or loses its electron. I made them work out a few of them, we did 10, practiced using the shortcut electron configuration. Then I had them right on the board. Then we looked at this in terms of what would be the easier way to get to a noble gas. If you look at sodium, sodium has one dot, one outer electron. Well, he could actually lose this, and he's going to look like neon. Or he can gain 7 more electrons, and he's actually going to look like argon. So then I asked, which is easier, for it to gain 1 or lose 7? And it's easier for it to lose, not gain 1, but lose 1 or gain 7. And it's actually easier for it to lose this 1 and look like neon. When you lose, you become positive. And how many is it willing to lose? Well, it's willing to lose 1. So sodium, when it forms an ion, forms a positive 1 ion. Oxygen here, can you see that he already has 6? So he could lose 6 and he'd look like helium, or he could gain 2. If he gains 2 here, then he's actually going to look like neon, and that's a noble gas. So what do you think? Lose 6 or gain 2? It's going to gain 2, so when you gain electrons, you become negative. We say this has a negative 2 charge. It's opposite what our brain wants to think from math. When you lose in math, it's negative, but when you lose in science, because you're losing electrons, it's actually positive. It's kind of like if you lost something negative in your life. If I were to lose the test the day before, that would be make you kind of positive about that. What about argon here? He's got 8, so he doesn't want to gain or lose, so his oxidation number would be 0. Aluminum, 2 plus 3 is 3. 2 plus 1 is 3, so it's got 3 valence, so it can either gain 5 or lose 3. He would prefer to lose these 3, look like neon, and therefore he would make a positive 3 charge. Look at nitrogen. Nitrogen's sitting at 5. He actually wants to gain 3 electrons. When you gain, you become negative. Makes a negative 3. Chlorine here, we're at 7. 2 plus 5 is 7. So he could lose 7 or gain 1, and when you gain, you become negative. He makes a negative 1 oxidation number. Magnesium, he's got 2. So if it wants to lose these 2, when it loses the 2, when you lose, you become positive, and it'd be a positive 2. Now, iron's a little weird here. So I've got the 3 kind of weird ones at the end here. Iron, notice he only has 2, because again, you're looking at the outer energy level, not the third, but just the S's and P's, if you think back to the dot diagram. So he would like to lose these 2, so he could be a plus 2. But there are some irons that are a plus 3. Now that's weird, and I'm going to show you how you're going to know, but a plus 3, sometimes what happens is sometimes it will lose these 2, and then it'll lose 1 more, and that'll make it lose 3. And the reason this is more stable is because, remember, we want 10 in the D's, but 5 in the D's makes it pretty kind of cool. So when you start dealing with the D, guys, they get weird, and you get more than one choice for oxidation number. So iron can actually be a 2 or a 3, and that's the reasoning why. If you're not understanding the reasoning why, then it's okay. I just want you to know that iron can be a 2 or a 3. If you look at carbon, carbon has 2 plus 2 is 4. Well, you're trying to get to 8, so you could either add 4, which will make it a negative 4, or you could lose 4, which will make it a positive 4. But carbon actually is a non-metal. If we go back and look at the previous slide, it says that all non-metals form anions, which are negative ions. So since carbon's a non-metal, he actually is a negative 4. And silver, look at it, one of the exceptions. Notice we put one in the S and put it into the D. Silver actually will lose this, and he doesn't lose any of the D's because the D's are already full. Silver is always a plus 1 oxidation number. So that's how you determine oxidation numbers. You're just looking at the S's and P's and looking to see if they want to add electrons. If they add them, then they become negative. If they lose them, they become positive. But just like I showed you with the dot diagram, I showed you a trick on the periodic table. There is a trick for these as well. we pull up your periodic table. You're going to want to label these on your periodic table. Everything in the first family all form +1 oxidation numbers. Everything in the second family forms a +2 oxidation number. We're going to skip over here in the boron family now. They all form +3. Carbon is a very weird family. They could be a +4, they could be a -4, or they could be a +2, because sometimes they only lose. So this is the whacked out family here. Here we did nitrogen. These are actually -3s. Oxygens, these are -2s. Then we did fluorine a while ago. He's a -1. And then the last family is 0. Look at the pattern. 1, 2, 3. Those are all positive because metals are positive. Then the weirdo guys, 4 and 2. Then it goes -3, -2, -1, and 0. Now silver we just did. Silver, and I would like you actually to physically write this on your periodic table, is always a +1. Always, always, always a +1. Silver is always a +1. Okay. The other guys, they're not always anything. Okay. But they do have a default setting. They're mostly 2 unless I tell you otherwise, except for silver. So unless I say it's copper 1 or it's copper 4 or it's it's chromium 1, chromium, it's always going to be a 2. It's like a default setting on your computer. The default's to 2. If you don't know what to make it a 2. But it will tell you, it's going to tell you actually in the form of a Roman numeral. We use Roman numerals for the middle guys and then this weirdo family here to let us know what number to use for oxidation. So I'm going to teach you how to write a formula and how to name a formula, and I have 2 ways to do it. The next part of the PowerPoints go through that, but rather than go through those PowerPoints, I'm going to show you and then let you decide which way you want to write a formula. If we were getting ready to write a formula, I'm going to do some examples, probably the same ones I did in class. I did sulfur and aluminum. I did lead. Now lead is in that weird family, so I have to tell you which lead to use. And so the way I tell you which lead to use, I give you a Roman numeral. And I and a V makes 4. So I want you to use lead 4. That's how you're going to know which lead to use. And I want to do that with oxygen. And then I think I did magnesium. Doesn't matter if we do the same ones or not. With chlorine. And then I did nitrogen reacting with, let's do aluminum. I'm going to show you 2 ways. Either way you want to do it is fine. There's 2 methods. There's one called the algebra method, and then there's another type that is called, I call it the swap, drop, and reduce method. Actually on the PowerPoint it's labeled the easier method. So you can either do the algebra method or the swap, drop, reduce method. I'm going to show you both. We're going to do algebra method first. First thing you do is you look and find out what each one's oxidation number. Like on the periodic table, we would look for sulfur. He's a -2. This is a +3. Those are numbers that we just wrote. This lead, in order for us to tell, it is a +4. This oxygen's a -2. This magnesium is a +2, this chlorine's a -1, this nitrogen's a -3, this one's a +3. Okay, so once you figure that out, you can figure out your cation and anion. Your cation is the positive one, your anion is the negative one. You always write a chemical formula with the cation first. The metal must always be written first. Very, very important. Like when I get mail from my husband and I, my husband's name is always written first. It's always Bill and Monica Smith. It's never Monica and Bill Smith. So the metal is always, like there's a marriage here, the metal's always written first. So we're going to write over here, we're going to do chemical symbols. It'd be Al, I'm going to write his charge as a +3, and we've got sulfur that is a -2. Okay? So what we're going to do now is that these need to cancel out with one another. Well, a positive 3 and a negative 2 do not cancel out with one another. So I got to find a common multiple that 3 and 2 will go into. And I'm going to use whole numbers as subscripts that are going to be written down here. What is a number that 3 and 2 will go into? Both 3 and 2 will go into 6. And we're going to ignore the fact that they're different signs right now. I'll show you something. So 3 will go into 6 how many times? It will go in there 2 times, and 2 will go into 6 3 times. So the formula gets written as Al2S3. No positive, negative. Here's why that works. You can multiply this. Positive 3 times a negative, positive 3 times a 2 is a positive 6, and a negative 2 times a positive 3 is a negative 6. Can you see those cancel out with one another? And that's why this works. This is my answer here. Alright, let's look at this one. This one is Pb was a plus 4, and oxygen, we always put the cation first, the positive one, so we put him first, minus 2. The common number that both of them will go into actually is 4. 4 will go into 4 one time. 4 will go into 2 2 times. So the formula is Pb. We do not write ones. If you feel like you have to write a 1, write a 1, but it's understood. PbO2. Just like in algebra, you don't put a 1x, you just put x. We don't put a 1. So there's PbO. For magnesium is a plus 2. Chlorine is a minus 1. Common number that they'll both go into, that will go into 2 one time, and this will go into 2 2 times. BMgCl2. Got this one. Aluminum is going to be written first because he's the metal. Metal has to be written first, even if I switch it up on you. And then nitrogen is the non-metal. And this is a positive 3, and that's a negative 3. They're already canceling one another out, so the number they'll both go into is 3, so it'll be 1 and 1. It'll just be ALN. Okay? That's the algebra method. You find a number that they'll both go into, and that. So that's a really easy method to do. So if you click through the next PowerPoint, I'll click through it in this video in just a second. It'll have that, but if you'll download the PowerPoint, you'll have that steps if you like the algebra method. Here's the swap drop method. I'm going to use the same ones as in examples. You're still got to write your cation first, and you still write its charge. You write your anion second, you still write its charge. Once that's written, you completely ignore the signs. The signs basically kind of disappear. The 3 goes down here, and the 2 goes down here, and it becomes Al2S3. If this reduces, you would reduce. It's called the swap, drop, and reduce method. 2 and 3 do not reduce, so we'll leave that alone. We'll look at this one. We've got Pb plus 4, oxygen minus 2. Ignore the signs and move the numbers. There, it makes that 4 go there and that 2 go there. Pb2O4. Well, this is a 2 and a 4, and guess what's going to happen here? They actually reduce. It's like 2/4 is 1/2. So this is not right. This is actually correct. So if you swap and drop, if you like this method, it's swap, drop, and reduce. Okay, this one here, if you'll notice, same thing. Mg is a plus 2. Chlorine is a minus 1. This 2 will go here. That 1 will go there. And it becomes MgCl2. Again, we don't have to write those ones. Alright, aluminum, which was a plus 3. Nitrogen, which is a negative 3. If you do the swap drop method, let me just show you 3 here and a 3 here. Becomes Al3N3. Those would reduce down to just ones. So it's just easier. If they're the same number, they automatically become ones and cancel each other out. So that's called the easier method or the swap drop, but you got to make sure you reduce, because if you give that non-reduced answer, it's going to be wrong. Okay? And then we learn how to name them. To name them, you write the name of the metal, because you know the guy never has to change his name when you get married. It's always the girl. So the non-metal is like the girl here. It's got to change its last part of its name. The first part, the sol, stays the same. This becomes sol, and it becomes fide, sulfide. That's an F, sorry. This would become lead oxide. Notice, I'm just taking like the first syllable and then adding I to it. This would become magnesium chloride. And this would become aluminum nitride. Whoops, almost misspelled it. IDE, all of these are IDEs. And that's pretty much the lesson that you learn. There is a worksheet over there. I've uploaded the worksheet to Edmodo. So if you're absent and you are watching this, you want to go ahead and start working on the worksheet, you can print that out at home and work on that. If not, you can come in the morning and see me and pick up the worksheet. It does have a front and back to it. And there is a quiz over this next time. So let me click through the rest of the PowerPoint. In order to write a chemical formula, there's the algebra method. Arrange your elements so the cation always first. Find the oxidation of each. The sum of the charges must equal 0, therefore you must find a common. Back in my day it was called denominator, but it's least common multiple, I think now. You place these multiples as subscripts, and we're going to work on the polys the same way. If you don't like that method, here's the easier way. Arrange them for the cations always first. Find the oxidation and number of each. Ignore the signs and switch the numbers. Be sure to reduce if possible. Same numbers become understood once. So that's everything that I just did. Polys are going to work the same way, but you must add parentheses. We'll talk about polys. You guys did not miss the poly lesson. We're doing that next time. Okay, and then to name them, you write the name of the metal, you change the ending of the nonmetal to IDE, such as sodium chloride. And this one would be magnesium oxide. And that's all the lesson. There is more on the PowerPoint, but that's all the lesson that we learned that day. Actually, I did talk to him a little bit about this. We'll talk a little bit more. If you come in class, well, I'll go over this with you, but the ones in the D's that I said, they're mostly 2. The way you're going to be able to tell on the worksheet and stuff, they're going to have a Roman numeral. So if it has a Roman numeral 2, that means to use it as a 2. If it has a Roman numeral 3, that means to use it as a 3. So the Roman numeral is what you'll use, and if there is no Roman numeral, you'll default to 2. So if you do download that worksheet, that's what that would be. So copper could be a 1 or a 2. We'll talk about some of these. Lead could be a 2 or a 4. And tin could be a 2 or a 4. There's a bunch of others. Most of those in the transition elements have more than one oxidation. And how are you going to be able to tell? Because it's going to have a Roman numeral. So you don't have to worry about it. It's going to have a Roman numeral. Except for silver, and silver is always +1. Hopefully you learned something from this. I'm tired of teaching the computers, so you guys have a good evening. So I'm going to stop this PowerPoint. And I'm going to stop this recording.